This project is a collaboration of the University of Missouri, Kansas City, U2D Incorporated, Kansas State University Semiconductor Materials and Radiological Technologies Lab, and Radiation Detection Technologies Incorporated. The Neutron detection system starts with a microstructured neutron detector developed at Kansas State University and manufactured by RDT. The Bluetooth transmitter was developed at University of Missouri, Kansas City and is manufactured by U2D. The combined system is capable of counting neutrons and transmitting the counts to a mobile phone. As a test, the lightweight Neutron system was attached to a DJI Phantom 1 Quadrotor and flown inside the reactor bay of the Kansas State University Triga Mark II research reactor to test how the system can find neutron sources in an environment with low neutron background counts. To the right is the mobile phone showing the count rate from the Neutron system. The counts will appear on the right edge of the screen as they come in. On the left side of the screen is the counts per second scale, which auto-scales, so as the count rate increases, the scale on the left side will change to keep the maximum count rate from going off screen. There is a small californium neutron source in one of the 3 metal boxes on the floor. We see the count rate increasing as the quadrotor drops down and passes the first box. The count rate increases as it passes the second box. And drops again as the quadrotor goes by the third box. Box number 2 is of interest, so we return for a closer look and land on top of box number 2. The auto-scaled count rate goes high and stays high until the quadrotor leaves the vicinity of box number 2. Now we will check the boxes. Box number 1 is empty, box number 3 is empty, and the source is in box number 2. This scene highlights the maneuverability of the quadrotor as it flies through the reactor bay looking for the same small californium source. As before, the auto-scaled count rate goes high and stays high when the quadrotor lands near the source. Here we use the quadrotor near a large californium source which is shielded but still has some background neutron counts. When the source is raised out of the shielding, we will see the auto-scaled counts increase and stay high until the source is lowered back into the shielding. The quadrotor remains some distance from the source, but the strength of the source keeps the count rate high. This technology could be used in case of a nuclear accident to map out radiation sources in an area where there is significant neutron background, could be used to find neutron sources in general, or could even be used aboard a Mars rover to find buried ice which gives off epithermal neutrons. Now, as the source is lowered, the count rate drops and the display rescales back to the background level. This concludes the test.